Alright, so today we are talking about the development of the atomic theory. We're going to talk about the history and who helped develop it. So, through this presentation, we're going to get through number 1 today, so the development of the atomic model. Then in the next lecture, we'll talk about the atomic structure. And then we'll talk about the isotopes and average atomic mass. And then finally, we'll be talking about counting atoms and the mole. So first, we're going to talk about the development of the atomic model. So early thoughts on matter. So our early philosopher, we have Demarcus, who was born and died roughly in 1460 BC. He decided or discovered that matter was influenced by natural laws. Along with his teacher Luponus, is considered one of the early atomists. He said that matter was made of small individual particles. And then we have Pluto, who came up with the idea of Timaeus, a dialogue that proposed that the universe was made of 4 elements that were in consistent motion. Pluto's lived around 1427. And then we have Aristotle in 380 BC, and he said that matter is continuous and continued the idea of the 4 elements and added a 5th element called ether. His idea of matter was accepted up until the late 1700s. So those are our 3 early philosophers, and then we're going to talk about our beginnings of the modern atomic theory. So in the 1790s, qualitative analysts began with improved measuring equipments. So chemists began to study reactions, and Anton Levester came up with the law of conservation of mass. The thought experiment demonstrated that any chemical process that all matter was conserved. So the law of conservation of mass states that matter cannot be created or destroyed during ordinary chemical reaction or physical change. Atoms can just be rearranged, and we see that today as still being true. So 2H2O plus 2O2 makes 2H2O2. So we have 4 atoms of hydrogen, 2 atoms of oxygen, and then we have 4 atoms of hydrogen and 2 atoms of oxygen after the reaction. Then John Dalton came along, and he helped turn Damascus' idea into scientific theory in 1808, with several points known today as Dalton's postules. And those are 4, so we have 4 points. All substances are made of tiny individual particles called atoms. Atoms of the same element are identical. The atoms of one element are different of those of another element, so hydrogen is not the same as oxygen. Atoms of different elements can physically mix together or can chemically combine in simple whole number ratios to form compounds. And then finally, chemical reactions occur when atoms are separated from each other, joined, or rearranged. Atoms of one element are never changed into atoms of another element. And that goes back to the idea of if matter cannot be created or destroyed. So, John Dalton's atomic theory, he proposed a billiard ball model where an atom was thought of as a uniform particle of matter. Not all aspects of Dalton's theory have been proven correct, right? Now we know that it's not really a billiard ball. It looks a little bit different. It's described as soluble, indivisible particle of matter. Then we have the discovery of the electron by J.J. Thomson in 1897. He used cathode ray tubes to study electricity and matter and revise the understanding of the atomic theory by processing that the atom can be subdivided. Below is the example of the tube that he used. So he had a slit, a positive plate, and a negative plate in the anode, and then a vacuum pump in the cathode, and then high voltage was pumped through. So the cathode ray experiment, right, you can see he introduces the equipment and then he moves on. We're not going to watch the videos, you can look them up if you're interested. So the observations and conclusions of this experiment is an object placed in the tube caused a shadow, a paddle wheel between the electrons moved, and then the ray was deflected with negative end of the magnet and attracted to the positive end of the magnet. Particles of the cathode ray have mass, so our conclusions were, and then the particles are negative and they are very, very small, and since neutral atoms contain negative electrons, hence had to have positive particles in that atoms. And electrons cannot account for all of the mass, right? So we discovered that this ray had mass and then it had smaller parts. So we discovered the electron and therefore eventually the proton. So Dalton's model versus J.J. Thomson's model. Dalton considered the atom to be solid and indivisible. However, with Thomson's experiment and the discovery of electrons, Dalton's billiard ball model was amended to the plum pudding model. So this model was a solid particle with charged particles and smaller negatively charged particles called electrons embedded throughout. So it's a one giant positive molecule, and then the electrons are embedded within. Oops. So the oil drop experiment was discovered in the 1907 to 1913 by Robert Millikan, and he designed an experiment known as the oil drop experiment. That further investigated the nature of the electron. So an atomizer would spray a mist of oil into a closed chamber. Two parallel metal plates would obtain a positive and negative charge with an electrical current, and then were used to manipulate the oil droplets as they fell through the chamber. So we sprayed a mist in, and then we used positive and negative charges to arrange the oil droplets. So what did Millikan notice with these observations? And it was the mass of a single charged oil droplet was calculated by how fast it fell. The voltage needed to suspend a droplet in the chamber was used with the mass to determine the overall charge of the droplet. The charges on the oil droplets were calculated to be in multiples of 1.602 times 10 to the negative 19 coulombs. The information was used to calculate the mass of a single electron, which was found to be approximately 1 in 1,840ths of the mass of a hydrogen atom. Knowing the mass of an electron led to the conclusion that a proton was far more massive than an electron. We're not going to watch the video. You can watch it online if you want. So then Ernest Rutherford came around in 1911 and used the gold foil experiment to study the atom. Alpha particles were fired at a thin sheet of gold foil. Most particles passed through the foil, however, some were bounced back or deflected in a different direction. Rutherford's hypothesis suggested that the atom must be made of mostly empty space, allowing most of the alpha particles to pass through the foil, further suggesting that a tiny core or a nucleus contained most of the mass of the atom. So conclusions from the gold foil experiment. So the nucleus is very small and it is very dense, and the nucleus is positively charged. So we went from the billiard ball model from John Dalton to the plum pudding model that was still mostly a solid matter with negative electrons pushed inside of it. And then we go to the nuclear model by Ernest Rutherford, where the protons are a dense, compact area, and then the electrons are out around it. Then we have Bohr's model and energy. So in 1913, Niels Bohr expanded on Rutherford's model by theorizing that the negatively charged particles exist in a specific orbit. So this developed in relation with the study of the hydrogen emission spectrum. So we can look at the energy spectrum of hydrogen and start identifying where these electrons sit. In the early 20th century, several scientists, including de Broglie, Heisenberg, and Schrödinger, elaborated on Bohr's orbitals, described the regions that the negative particles of the atom exist as orbitals. So there are different orbitals that the electrons sit in around the nucleus. So now we can see the development of the atom, right? We started in 400 BC with Demarcus, and then we moved to the billiard ball model, then the plum pudding model, then the nuclear model, then we go to the orbital model, and finally we can see the orbital model has some tweaks, and that is what we mostly use today. So we will end here, and we'll see you next time. Don't forget that we have a quiz on Friday.